Hello, welcome to the Remote Sensing tutorial course. I'm going to present the first chapter, which is a general introduction to the basic principles of remote sensing. My name is Antoni Broquetas. I'm a telecommunication engineer. My PhD subject was microwave imaging for biomedical applications, and in the last 25 years, my main activity as professor of Polytechnic University of Catalonia has been teaching and doing research on radar systems, imaging, and remote sensing. This tutorial is organized in 5 modules, each one containing 2 chapters. In this way, this introduction chapter is part of the first module, together with Earth Observation Tools chapter. The following modules address different types of sensors and their applications: synthetic aperture radars, microwave radiometers, multi- and hyperspectral sensors, and LiDARs. This course is intended mainly for graduate students with a basic background in physics, mathematics, or engineering. It contains reference anyway to bibliographic sources, allowing to complement the lessons contained. This tutorial has been developed free of charge for educational purposes only and without any commercial interest. Some images and figures of this tutorial have been reproduced from open sources and are cited accordingly, unless they were created by the authors. If you believe any material shown may be infringing a copyright, please tell us to remove it or to take appropriate action. This slide shows the introduction outline. We will begin with the definition of remote sensing. Then we will actually outline some historical milestones. We will distinguish between active and passive remote sensing techniques, and we will actually consider some particularities of electromagnetic spectrum, different bands, and how can actually be expressed electromagnetic waves mathematically, what kind of observable parameters we can actually measure, and with special attention with the wave-matter interaction mechanisms, because these are basic for remote sensing information obtention of the observed surface. Some application examples and characterization of the imaging process in terms of metrics, quality metrics, and finally a consideration of different steps in the remote sensing value chain, because remote sensing is both a collection of science and techniques and also an emerging economic sector. What is remote sensing? Well, we can consider the science and techniques with a common purpose of obtaining information about the physical world from distant platforms, usually aircraft and satellites. In the right hand image you have an example of remote sensing product. In this case we have soil moisture parameter or values which are obtained over Australia after a rain event. This slide shows some historical milestones of imaging and remote sensing technologies. The first milestones are actually important steps in imaging, from early imaging devices like camera obscura, the invention of conversion lens, telescopes, and the first emulsion, photographic emulsion, able to register images, X-rays as a first example of non-visible or non-optical portion of the electromagnetic spectrum being used for imaging. TV cameras and optical holographies are also important steps, with the invention of optoelectronic devices, lasers for example, and also in the 1950 the beginning of the space technology with the launch of the first satellites was really important, because that was actually the opportunity to place sensors at very high altitudes with important coverage of the Earth. The first example of it was Tyros-1 meteorologic satellite, and also at the same time the first LiDAR systems were developed for atmospheric sounding, And the 1970s was a really important decade for remote sensing, because many important instruments were developed at this time, and with large satellite programs, in some cases like the Landsat, which was a multispectral, very ambitious program for this time, and also the first spaceborne radars on board of Skylab and CSAT satellite, and first microwave imaging radiometers on board of Nimbus. From this time up to now, in the last decades, and actually a kind of explosion of many instruments and missions, remote sensing missions, have occurred. And actually there are some missions mentioned here, but this is just the tip of the iceberg. There is a lot of more, and actually we can maybe outline a few of them. For example, the development of hyperspectral sensors, missions also for planetary exploration, so not only the Earth is important in remote sensing, invention of or development of new concepts like the interferometric radiometers, interferometric synthetic aperture radars for different applications, and so forth. The slide shows two categories of remote sensing instruments, active and passive. Active techniques are based on providing the illumination by the sensor itself. So the sensor actually sends its own illuminating energy in terms of radar pulses or laser pulses. This confers some advantages of independency of external illumination by the sun, for example, but on the other hand actually require high power. In the case of passive techniques, which is example of it are multispectral, hyperspectral sensors or microwave radiometers, the sensor operates based on either external illumination like the sun, or receiving the spontaneous thermal self-emission of materials, and for this reason the power consumption is rather low. The slide shows an example. Actually it's the first spaceborne remote sensing mission. This is TIROS-1 meteorological satellite. The satellite is a small cylinder containing a zenithal observation TV camera and the support subsystems. And on the right hand you can observe the first image, actually a television picture obtained from this satellite showing the cloud distribution on the Earth. A more recent example, actually it's a very recent one, is the Sentinel-1, which is shown in the left part of the slide in the anechoic chamber test of the radio frequency parts, including the antenna which is deployed here, the array antenna. And in the right part of the slide you can see a detail of the first image, which was taken on April 2014, and this corresponds to the city of Antwerpen in Belgium. In this case we can observe a basic picture actually showing the interaction of an external illumination. In this case the sun is providing the illumination, sunlight is reflected and scattered on the Earth's surface, and a satellite's sensor actually is picking the reflections and the scattering of the sunlight over the Earth. So, and this shows the basic requirements of remote sensing. First, we have to obtain information, and this is based on the wave-matter interaction, scattering, reflection taking place on the surface. But secondly, and very important, this information must travel from the scene to the remote sensing, normally a satellite which can be hundreds of thousands of kilometers away. And it happens that electromagnetic radiation is able to sense physical properties of materials, so it's actually obtains information from those surfaces and at the same time it propagates very efficiently through space, so actually satisfying the two fundamental requirements of remote sensing. And for this reason, most of instruments are based on electromagnetic radiation. Let's take a look about the electromagnetic spectrum. What you can see here is the classification of different bands of the electromagnetic spectrum, in this case increasing frequency from the left to the right, radio, microwave, infrared, visible, ultraviolet, X-ray, and so forth. Just below the names of the bands you can see some numbers which are the wavelengths in meters corresponding to the different spectral regions, and you could see how large is the dynamic range. Actually, we start from wavelengths of kilometers, that corresponds to radio waves, medium or short waves, and then at microwaves we are already at a submetric region, which means centimeters, and we go into micron scales in the infrared and visible, and lower scales when we go at higher frequencies. And we have some icons here which are representative of objects with sizes which are comparable to the wavelength. And for example, this means if you want to be especially sensitive to a kind of object, you have to choose a wavelength which is in the order of the size of this object. For example, at microwaves, wavelength is in the order of the sizes of leaves, and this provides the capability for microwave sensors to actually obtain information about this kind of a scale of structures of bodies. For example, we can classify different types of globes according to the scattering characteristics of these surfaces. If we want to look at thinner details of matter, we have to increase frequency and decrease wavelength accordingly. So if we want to look at scales of microns or submicron scales of matter, for example macromolecules, chlorophyll, for example, in plants or vegetation, we have to use visible or infrared region of the electromagnetic spectrum. And if we want to go below and obtain information at molecular or atomic level, we have to increase even more our frequencies. Actually, in remote sensing, the range, most of instruments use ranges of between microwaves and a visible region. And the reason for that is mainly the atmospheric attenuation of the electromagnetic spectrum. This graph shows the transmissivity of the atmosphere in clear conditions, this means without clouds, in zenithal observation, depending on the wavelength we use. In this case, the wavelength is decreasing from ultraviolet region, visible, infrared. At this far infrared point, we continue with the lower graph at higher and longer wavelengths, up to millimeter and centimeter scale, which corresponds to microwaves. And you can see here that we have two wide windows we can use. One is in the visible region. The second wide window is at the microwaves. These bands here is the typical microwave bands that radars and radiometers use. And in the intermediate region, which is infrared, which is really a very wide region with many difference of scale and wavelengths and frequencies, you can see there is a lot of bands with we have either a window or an absorption region. So we have to be very careful working in the infrared to pick the correct window. Otherwise we will get no information of the surface, although we might get information on the gases of the atmosphere where this interaction is taking place. This slide shows the set of Maxwell equations combining previous findings of Gauss, Faraday, Ampere and other scientists of his time. They are very relevant in remote sensing since they relate the observed electromagnetic fields to basic material, electric and magnetic properties, allowing to obtain quantitative information of distant bodies and surfaces. These parameters of materials are the electric permittivity, this epsilon, which models the changes in the internal charge distribution caused by an external electric field, for example, this product here. Also the electric conductivity, sigma, which accounts for possible currents developing inside the material when an external electric field is applied. This J term here is the current flux inside the material. And finally, the magnetic permeability parameter, this mu parameter, which models the alignment of the atomic magnetic dipoles when an external magnetic field is applied over the material. Actually, you can observe the proportionalities of electric, magnetic flux with the external electric and magnetic fields, and these parameters, epsilon, permittivity, and mu, magnetic permeability. Also, you can observe also the proportionality between the current and the electric field according to the conductivity of the material. Actually, you can notice that epsilon and mu are often expressed in terms of relative permittivity or permeability, and this is relative to the vacuum values epsilon 0 and mu 0, which are expressed here in the slide. Let's take a look to the Maxwell equations involving time derivatives and of magnetic and electric flux densities. Let's take a look to these two equations of the set of the Maxwell equations. In the left, we have actually two versions in the slide of Maxwell equations. In the left, we have the set corresponding to arbitrary time evolution, time variations of the fields. In the right, we have the same set of equations, but in this case, this corresponds to a particular case of time evolution of fields, which is harmonic or sinusoidal. This is very important in practice because many of the signals we actually use in remote sensing, particularly active remote sensing, are harmonic variations of the fields. And this is normally expressed in this exponential term A plus J omega t, where omega is the pulsation or angular frequency expressed in radians per second. These Maxwell equations, either in the arbitrary time or harmonic case, actually tell us that for static conditions, electric and magnetic fields are independent. But in the case of changing fields or time evolution, these fields, electric and magnetic, become coupled. So this means, for example, a change in the electric flux actually is causing a magnetic field line which is surrounding the area of where this electric flux occurs. This is the meaning of this curl operator here. This means the lines are surrounding the area of the source of this electric field change. The same happens when the magnetic flux is changing. It induces also an electric field surrounding the area of the change. Combining both expressions, we obtain a wave equation. Let's take a look to the wave equation in free space conditions. So actually, solutions to this equation, either in the arbitrary time variation or harmonic time variation, correspond to waves that can propagate in space without any material support. There are many solutions depending on the selected coordinate system and boundary conditions, but the simplest one in the harmonic case is a plane wave. You can see here what is mathematically a plane wave is only have changes along time, and in this case the direction of propagation, which is in this simple case is the z-axis. Also, this is for the electric field. The magnetic field shows the same kind of behavior, actually is proportional to the electric field, but with a constant of proportionality which is called the medium impedance. This medium impedance, eta parameter, is very important in remote sensing because it corresponds to the balance between, or the ratio between, the electric field and the magnetic field component of a particular wave. And in case of changing the medium, for example in the interface of air and the ocean surface, the medium impedance of air and water are very different, dramatically different, and this is going to result in a strong reflection. This is why this parameter is so important in remote sensing. Changes in impedance account for a scattering and reflection of waves when different materials are encountered. If we take a look to the time evolution of the plane wave example, you can see here the harmonic evolution, which is obviously happening because this is we took this solution, the harmonic solution, and this is actually the solution, the time evolution for a fixed position, for example z equal to 0. If we fix time, we freeze time, we take a photograph, if you want, of the fields, and we observe the spatial evolution of the fields along the z line. It is also a harmonic evolution, a sinusoidal evolution, but with a different actual period. So if the time period is capital T, which is the inverse of the frequency of the signal, the spatial period is lambda, and this is the wavelength, and the relationship between the spatial period and the time period is just the velocity of propagation of the wave, which is normally expressed as c, because c is the speed of light constant, and this value is actually related again to the material permeability and permittivity constants. This factor comes from the wave equation. This constant of proportionality relates the time variation, second derivative of time, with the second derivative of space, which is this now Laplacian operator here. Finally, another interesting parameter here is the wave number, again related to the constitutive parameters of a material and also the pulsation frequency of the signal, of our excitation of fields. And this wave number parameter, also related to the wavelength, is actually expresses the phase which is lost by the wave when it's traveling through a medium. Actually, this wave number has units radians per meter of traveled path. The slide in this case shows what are the wave parameters that we can observe in two actually types of signal. In this case, in the left hand, we have the case of coherent fields. These fields are normally provided by the sensor. It corresponds to an active sensor. It is a deterministic field. And what are the parameters we can observe? Well, we can observe amplitude, for example, of this field. If this corresponds to a pulse of energy, for example, emitted by a radar or a LiDAR, actually we can measure the delay of the echo, this T sub r parameter here, which is indicating the distance traveled by the wave. Another parameter which is interesting in some applications is the phase. The phase is the angle of at a point of reference, for example, the leading edge of the pulse or the center of the pulse. We can measure the phase, and this phase value here is indicating with extreme accuracy the delay and the path traveled by the wave. And this is important in certain applications, measuring the distances with a lot of accuracy. In the case of precision, in the case of this phase is changing with time, we call this a Doppler shift, and it is also interesting to measure the speeds and other parameters of the surfaces. Also, we can measure the polarization of the field, so the fields can be oriented along the Cartesian axis, x, y, or just another arbitrary axis, and it can also happen that both the x and y components of the field are not in phase, and in this case the field is actually rotates following an ellipsoidal shape, like in this figure. In the case of incoherent situations, this corresponds to passive systems where there is no actually transmission from the sensor. Now we are relying on natural sources like the sunlight, or for example the thermal spontaneous radiation of materials, and in this case the waveform which is transmitted is actually random, and this corresponds to an incoherent field. And this is, for example, the shape of a field evolving with time in these cases. What can we measure here? Well, we can measure power. We can measure a spectrum if this actually power is unevenly distributed along the spectrum of waves. And we can still measure the polarization of the electric field, for example. Let's see some examples. In this case, we have an optical image obtained by a multispectral sensor. It is the MODIS mission. In this case, the sensor has a medium resolution, but it is enough to obtain very interesting images, in this case corresponding to forest fires in the north of Australia. This image is a radar amplitude image. The amplitude shows some details of topography, mountains, a river here. But let's take a look to the phase of the image, actually to the phase difference between two consecutive images of the two similar satellites. In this case is EARS-1 and EARS-2 from ESA. And the phase information in this case shows actually the topography. And this phase information can be processed in such a way we can obtain digital elevation maps, which are really important products for planning and any infrastructure development. This image corresponds to another observation parameter, which is the polarimetry, or the polarization of the scattered fields. In this case, we have combined different polarizations. HH means we transmit in horizontal polarization, and we receive with a radar in horizontal polarization. And these components have been combined in the so-called Pauli decomposition, which means if we add these two components, we obtain basically the contribution of single scattering or three bones scattering. The red components corresponds to an even bones scattering, so double reflection basically, and the green component corresponds to volume scattering, which is particularly strong in vegetated areas. So the colors in these images show us different scattering mechanisms, and this can be associated with different kind of infrastructures and covers on the terrain. Now, let's go back to the fundamental parameters, dielectric, permeability, conductivity parameters of matter, and let's try to apply these parameters to remote sensing image interpretation. This slide shows the permittivities, static permittivities of a group of materials, from low permittivity materials like air or low density foams, like this case here, where these values are relative to vacuum. So you could see air is essentially almost the same as the vacuum permittivity, which is exactly 1. Now we have here some solid materials, Teflon, some plastics, and some minerals, and you could see that the permittivity is increasing moderately up to some materials. For example, this rutile or titanium dioxide material has a strong, very strong permittivity values, and also some liquids like glycerin or water with so-called polar molecular liquids have also very strong permittivities. So what these permittivities mean exactly? Well, permittivity is the capacity of the material, or the charges, electrical charges on the material, to become aligned with respect to an external electric field material. This corresponds to a capacitor. This is just an example to understand what's going on with the dielectric polarization. We apply, we introduce a dielectric inside the capacitor plates, which produce a more or less constant electric field. And what happens is the electric flow electric flux density increases due to the polarization of the electric charges which are trapped inside the dielectric. These charges are not abandoning the dielectric, but actually reinforce the electric flux. And for example, with this rutile, this reinforcement is in the order of 100 or almost 200 in some cases. So it can be really large. So a higher permittivity material increases the charge and energy stored in the electric field in the material. What about the conductivity? The conductivity was the capacity of the material to develop electric currents inside the material in case of it is of electric field excitation. And actually these electrical currents are responsible for losses, typically in dielectrics, and these losses can be modeled, including an imaginary part in the dielectric permittivity of the material. So, for example, this imaginary part now includes a conductivity term, and this models in a very elegant way the losses of materials. Now, when this happens, the wave number becomes also complex. The wave number has an imaginary part which is alpha, and this alpha is responsible for the wave attenuation. So alpha is actually an attenuation parameter which can be expressed in dBs per meter by multiplying by this constant here. And let's take a look to some values. Actually, we have chosen some materials here from very low conductivity, which is typically good dielectrics or insulators, very good conductors, which are typically metals, and some materials which are a bit in the middle, are not good insulators, either not good conductors, and they are considered semiconductors. For example, silicon is an example. There's also some materials, for example, wet soil is also here in the middle. It's not either a good insulator, not a good conductor, for example. Let's take a look to water. But water is pure. It is quite a good insulator, but if we include some small solutions or some ions inside, for example, the case of fresh water, it becomes much more conductive, and if the salt dissolved in the water has a quite important density, now it becomes almost a good conductor. Okay, what are actually the mechanisms for becoming polarized material in response to an external electric field? Well, there are many mechanisms. Some of them are really important in terms of permittivity, like the dipole orientation of molecular level of some liquids, like water, for example. You see here, these are atoms of water, molecules of water, and actually the hydrogen atoms are slightly positive and the oxygen atom is slightly negative. So in response to an external field, because this is a liquid, these molecules can rotate and orient themselves, and this is actually a coupling of energy between the inner electric fields and the external field applied. And strong polarization results from these mechanisms, and this polarization is only important at the low frequencies up to a range of microwaves, because this rotation of molecules takes some time to occur, so they cannot respond to extremely fast fields like the visible or higher frequencies. However, when we are above microwaves, still the water molecule can become polarized, and in this case the mechanism is not anymore the rotation, but it's the deformation of the molecule itself impacted by the external field excitation. And this deformation, or this elastic deformation of the molecule, it also takes some time, has some relaxation time to occur, and this means that this mechanism is not important at any frequency. It actually disappears for frequencies above the visible region. And then what is left? If we are in the ultraviolet, for example, what is left? We have lost the possibility of rotate, we have lost the possibility of elastic deformation. We have still the possibility to distort the cloud of electrons in the oxygen atom of the molecule, for example, in this example. So the cloud of electrons is actually responding, or is deformed according to the external field applied. And this is a weak mechanism, but a small permittivity results still in this case. If we actually express in a single slide all these mechanisms, we can show here the real part in black. The black line is the real part of permittivity of water, and in the blue line shows the imaginary part, or what is the same, the losses mechanisms expressed in terms of this imaginary contribution in the permittivity. And this is expressed in, with respect to frequency here, or if you want wavelength in the upper layer. You see here the visible region here indicated, and this is microwaves, this is ultraviolet region. And you see here, okay, for up to microwave frequencies, the molecular rotation is actually responsible for a very high numbers of permittivities. It's in the order of 80, 70 to 80, depending on the frequency, depending on the temperature. If we go beyond the microwaves, this molecule is not able to rotate at the rate of the frequency of the fields, but still we have a coupling which is not so important, but is still relevant due to the deformation of the water molecule. As you can see here, we have now permittivities in the order of 4 or 5 depending on the frequency. You see here the blue line takes quite strong values. This means we have quite a lot of losses inside the water. So this changes the rotation and molecular deformation. It's actually taking energy, actually dissipating a part of the electromagnetic wave going through the material, in this case water. And you see here some particular resonances of the molecule. These transitions here are typical of an oscillator, which is excited close to the resonance frequency of the oscillator. At this middle point we have a peak on attenuation here, which is shown here, and you see here several peaks which correspond to different elastic resonances of the water molecule here, up to the region of ultraviolet, where we have still electronic resonances, but you can see here the coupling or the deformation of the charges induced by the external field is very small now, and the permittivity is barely above 1, which is the value of vacuum. What happens with the magnetic properties of materials? What happens is the following. Most of the materials we encounter in nature, they have static and dynamic permeability constants which are very close to 1. So most of the materials, dielectric, metals, semiconductors, have very or barely or permeabilities which are extremely close to 1, so we cannot distinguish these magnetic properties of materials unless we use a very sensitive measurement system, which is not the case of very distant remote sensing systems. There are exceptions for that, of course. We have ferromagnetic materials where the internal magnetic dipoles at atomic level and also electronic spin level becomes extremely coupled with respect to external magnetic fields, and in this case the permeability increases dramatically from almost 1 to hundreds of thousands or even 1 million in some cases. But what happens, most of these materials are metals, and metals are very good reflectors of electromagnetic waves, so actually it's very difficult to use this property in remote sensing. Now, we have talked about materials, but what happens when we observe not a simple material, but we observe a very complex surface formed by several materials, and also with different shapes? So, for example, we have here sea water in the coastline. For example, we have here some land, vegetation, a house, cars, for example. And also we have double interactions, because some of these incident waves from the sun or a radar or a laser actually can impact on the land surface and suffer a double reflection on the vegetation or on this wall of this house. So what happens with these scatter fields? Where are going to be the dependencies of these fields on the basic parameters of the surface? Well, the scatter fields depend on the dielectric contrast between the air and the surface dielectric characteristics, the local incidence angle, the surface or roughness. It's going to play a very important role in microwaves, for example, and will depend also on the size and geometry of the object, the polarization of the waves, and the existence or not of multiple interactions, double or triple reflections. Let's take a look to some basic models in order to understand the mechanisms, the reflection and scattering mechanisms of the surfaces. We have a very simple model to start with, which is actually the interface between two dielectrics. We have a planar interface between two materials, one here with this dielectric and permeability constants, and material 2 with different values of epsilon and mu. What happens when we have an incident wave here, a plane wave, which is actually impacting on this interface between the both materials? Well, the Fresnel laws in physics and electromagnetics, what they tell us is we have a reflected wave which is actually going or traveling at a symmetric angle with respect to the angle of incidence with respect to the normal axis to the surface, and we have also a transmitted wave which goes inside the second material. And actually by using some properties of continuity of the tangential components of the electric and magnetic fields over this surface of interface, what is so-called the boundary conditions, actually we can calculate quite easily what is the magnitude of the reflected and the transmitted rays. Actually, in the continuity of the surface, the total wave, electric wave, which is the incident plus the reflection, must be equal to the transmitted one. This sign here actually means that the electric field is orthogonal, in this particular case, is orthogonal to the plane of incidence. The plane of incidence is actually the surface of the screen of projection, and you could see here the electric field is actually orthogonal to this plane of incidence. That is why this is this symbol is indicating this situation. And this is why in the case of the electric field which is oriented orthogonally to this situation, so vertically instead of horizontally, the expressions are different. But you could see here one can obtain what are the angle of transmission, this theta2, this is the so-called Snell law, and we can obtain the reflection and the transmission coefficients, which actually depends on the impedance of the medium 1 and 2, and actually depends also on the angles of the incidence and reflection. In the case of field which is parallel to the incidence angle, in the case this corresponds to a vertical polarization of illumination, we get slightly different expressions, but they are very similar in the sense that the reflection is actually proportional to the difference between the impedance of both media. And this was the case also in the previous expression. There are particular angles of interest, for example a critical angle of total reflection. This happens only coming from a higher density material to a lower density one, so higher permittivity to lower permittivity. This is not the case usually in remote sensing, because in remote sensing we come from air, which is a low permittivity, into a higher permittivity land or water material. So normally this is not useful in remote sensing. It's useful in fiber optics and other applications, but not in remote sensing. In the case of remote sensing, for vertical polarization, there is an angle which is really important. It is particularly important in microwave radiometry. In this angle, what happens is we have a total transmission and there is no reflection in the interface of both materials, and this happens for an angle which can be calculated with this expression here involving the ratio between the permittivities of both materials. Okay, let's apply these expressions to a simple case. Let's provide a electromagnetic wave with an excitation of amplitude equal to 1. This is an electric field which is depicted here in red, and this is impacting orthogonally to an interface of air-water. So this is a water surface. It's shown vertically here just for simplicity, but you can imagine that could be the surface of a lake, for example. And what happens here? Well, let's take a look to the permittivities. The permittivity of air is almost 1. Permittivity of water, we include the losses of water here, is 77 minus EA9, so very high permittivity compared to air. This corresponds to a 2.45 at microwave region, by the way. And what happens? We have a lot of contrast. The impedance of both mediums is going to be very different, and if the impedance are different, we have a strong reflection. And actually this green line here is actually showing the amplitude of a reflected wave. You see the amplitude is not the original one, but is almost 0.8, so it's very important. The reflection coefficient is 0.8 approximately. So most of the energy is going to be reflected due to the high contrast of dielectric permittivities. There is a small transmitted wave inside the water, but look at this transmitted wave here, and compare it to the amplitude of the incident wave. First, we are losing a lot of amplitude because most of the energy is going to be reflected. And also, when the wave evolves inside the water material, you see here the wavelength is much shorter compared to the air wavelength. This actually decrease in wavelength is on the order of the square root of the real part of the permittivity, so it's almost a factor of 9 in the case of water. And also an attenuation, exponential attenuation results. In the air the losses are very low, but inside the water are very high. So the attenuation which is responsible of this imaginary parameter is extremely strong, in the order of 2 dB per centimeter, and this corresponds to fresh water. For salty water, in the case of seawater, the attenuation is even higher. So in practice, water, it's not going to be penetrated in the liquid state, at least, at microwave frequencies. It could be penetrated at visible frequencies, for example, but not at microwaves due to these particular permittivity values. Okay, let's take a look in practice to a radar image, in this case synthetic aperture radar images, which was obtained by the shuttle imaging radar mission. And the image corresponds to the Nile influence area in Egypt. And actually what we can see here is, okay, part of this image is it corresponds to sand, so dry sand. In the case of dry sand, the permittivity of this material is very low. It's quite close to air, it's almost 2. We have also the Nile River here, which is this band here, this dark band, and we have also a bright area here, which is the area which is influenced by the Nile. This actually corresponds to the year flooding region, and this area is strongly cultivated, and also it contains some urban areas. If we take a look to the cultivated areas like this one, you can see here the brightness is much higher comparing to the sand covered area, and you could ask why is that? Well, let's take a look to the dielectric constant. The contrast between air and dry sand is low, so the reflection is not very important in this case. So this corresponds to a dark image because the reflected waves are not very high, they are weak. In the case of cultivated soil, the permittivity is considerable higher, so this means the reflection is also more important, so the echoes will be stronger compared to the sandy area. So okay, this is consistent with the reflection coefficients we have just seen. But what happens with water? With water, the permittivity is close to 70. Or real part of permittivity close to 70. This means a very strong reflection is happening here, according to the expressions we have seen. Now we should we should see here, in principle, a very bright band corresponding to the water surface. But it's not bright, it's dark. Why is that? Well, actually, this is consequence to the simple model we have used. We have used a model up to now based on a flat surface of observation. But in this case, in these images, some surfaces are flat, some surfaces are not flat. They contain a lot of roughness, particularly cultivated areas. And this is actually changing a bit the starting point of reflection between two dielectrics. So let's consider now the case of water. What's happening with water? Why, if the water is reflecting a lot, why is appearing dark in the image? Well, there is something we have to consider that we have not explained yet, is the fact that in synthetic aperture radar, the observation of the radar is oblique. So this means the radar is not observing from the zenith, is observing from one side of the image. In such a way, if the surface is flat, we have a strong reflection, but this reflection is going away, it's not coming back towards the radar. This is the reason why the water surface appears very dark in the previous image. Now, let's consider we include some roughness. Let's consider now, for example, a small roughness, small wave on the water surface of a lake or a sea, for example. Well, if we increase roughness, for example, the standard deviation of height is below lambda, but it's not zero, it's not much smaller than lambda. In this case, we have still a predominant scattering along the specular direction of reflection, but now this lobe is becoming open, and actually some side lobes appear, so some part of the signal can actually come back to the radar, although it will be quite weak. If we increase the roughness, so now the standard deviation of this surface observed is comparable to lambda scale. Now we have still a slightly concentration of the scattering diagram towards the specular radiation, but not so much, and actually we have a quite intense echo coming back to the radar. If we increase even more the surface roughness, in this case, for example, the standard deviation is much larger than lambda, then what happens is the scattering diagram is very open, is almost omnidirectional. We have lost this privileged direction, a specular direction, and this is called a Lambertian scattering situation, where actually the radar reflectivity does not depend very much on the angle of incidence. It depends a bit because of the effective area which is observed depending on the angle. And this is modeled by this cosinus square of lambda, but it's not very directional. Another situation that occurs when we observe natural surfaces is, in some cases, the surface has strong periodicities. This is the case, for example, of a cultivated area, or, for example, certain sea waves with strong periodicities. In this case, what happens is the echo signal, or the signal reflected, is actually a combination of the individual reflections of several wave crests, like these ones depicted here. And when we combine the fields, we have to combine amplitude and phases, and the phase of the fields can result in some cases in a positive interference of reinforcement, mutual reinforcement between these contributions, and in most cases these contributions will be out of phase, and when you add up a large number of these contributions, the result is 0 or a very small value. Actually, these are the expressions resulting, and when we plot this scattering behavior, what we discover is we have a very strong reflection at certain angles. The first reflection is at orthogonal or zenithal observation, but in oblique observation we have strong returns only when these surfaces become resonant, and then the returns of the single wave reinforce together. And you can see here a CD. A CD is also an optical case of this kind of surfaces, because the information is written here in a kind of a helicoidal track, and the distance between the radial distance of this track is very small, is in the order of the optical wavelength, and this is actually an optical example of this kind of situation. But you see here this difference of colors is actually how the light is decomposed by the different resonances which take place at different frequencies. So this resonant condition depends on the angle, but also on the frequency, and depends also on the periodicity of the surface itself. Actually, by the way, this can be used to decompose the light spectrum in different colors or different components, like a prism. So all these mechanisms, for example, on the ocean surface, the roughness and different periodicities of waves actually provide different brightness depending on the wind conditions and orientation of waves with respect to the sensor and so forth. In the case we have contaminants, for example oil contamination on the sea surface, the oil actually damps mechanically the roughness due to sea waves, so a lower roughness result in oil affected areas, and this is actually reflected or impacted in a very dark pattern. So this pattern actually corresponds to oil pollution. In this case, this is a radar image obtained by MBSAT corresponding to the Prestige tanker wreck near the Galician coast in Spain. Another parameter which is important talking about interaction between electromagnetic waves and matter is the size of the individual objects or particles. In order to understand the size dependency of electromagnetic scattering, we have plotted here a very classical result of the radar scattering or radar cross-section of a metallic sphere of radius A. What is plotted here is in the vertical axis of this graph we have the radar cross-section, which is, if you want, the radar brightness, divided by the geometrical cross-section of the sphere, PA square, and this is represented with respect to the size, the electrical size of the sphere, which is actually plotted in terms of perimeter, sphere perimeter divided by lambda. So what this means is if we are towards the left, the perimeter of the sphere is very small compared to the wavelength, so the sphere is electrically small in this case. In the center region, the perimeter is comparable to the wavelength, and in the right side of the x-axis, the perimeter is becoming electrically large. It's much larger than the wavelength. And you can take a look about the result in this black line of the radar cross-section of the sphere. You can distinguish three different regions. One region which actually results in a strong decay of radar cross-section when the electrical size of the sphere is small. So if the sphere is small compared to lambda, what this result is showing us is that the interaction between the wave and the object is very small, so there is a small reflection resulting in this case. Only when the sphere is comparable to the wavelength, there is a very strong interaction now between fields and the currents on the surface of the sphere, and in this case the sphere actually becomes a very strong radiator, very strong scattering object. And actually we have here some oscillations. This is called the Meyer region or resonant region, and this corresponds to a perimeter which is between 0.5 lambda and 10 lambda. Actually this mechanism here, or this actually oscillation mechanism here, is due or can be explained due to two reflections, two scattering mechanisms. One is the reflection on the front side of the sphere, and a second mechanism is actually correspond to a traveling wave which goes around the sphere and also is added on top of the frontal reflection. Because the length of these two paths are different, depending on the frequency, these two mechanisms reinforce or tend to cancel each other, and this explains this oscillation here, or this resonant condition. When the frequency is increased in such a way the electrical size of these spheres becomes large, the traveling wave, it's actually, the role of this wave is actually residual compared to the frontal reflection, and this becomes asymptotically converts to a value of 1, which means the radar cross-section of the sphere is equal to the geometric cross-section, or geometric area, projected area by the sphere. In the Rayleigh region, the sphere is actually, the scattering of the sphere is strongly dependent on the frequency. So at higher frequencies, the scattering increases substantially. In the optical region, the radar cross-section of this sphere is basically independent of the frequency or wavelength. This region has the name of, a low frequency region has the name of Rayleigh, because Lord Rayleigh studied for the first time this phenomena in the case of aerosols in the optical region. Let's take a look at an example of these different scattering conditions. This is just a photographic picture which shows the sky, the blue sky, and some clouds. And look at the colors. The sky is blue while the clouds appear black, white or gray. And why is that? Why the sky is blue? Well, the molecules of the atmospheric gases are smaller, or much smaller than the wavelength corresponding to the visible region of the electromagnetic spectrum. So they are in the Rayleigh scattering region. This means that the scattering is going to be much more efficient at higher frequencies than lower frequencies. And higher frequencies in the optical region corresponds to the blue color. What happens in the case of the clouds? Well, the cloud particles are basically very small water droplets, and the sizes are much larger than the wavelength and optical frequencies. This means these cloud particles are in the optical scattering regime, where the scattering is essentially flat or not depending on the wavelength, and so no colors in this case, only white. Well, these particularities can be used to observe cloud distribution, aerosols, pollution, dust present in the atmosphere, using, for example, optical radiation, in this case a LiDAR. A LiDAR is a laser which transmits pulses and receive the echoes reflected by the aerosols and particles in the atmosphere. So actually what you see here is the distribution of reflection on aerosols and clouds with respect to time, when actually these cloud distributions are progressing due to winds, are moving with respect to this beam. So the beam is fixed, and it's the atmosphere which is moving, and this is the time of the day. So along several hours of observation we can take quite a lot of information of the distribution of aerosols in the atmosphere. This vertical axis corresponds to height in hundreds of meters, and this is actually a reflectivity scale. Also, other applications of optical observation relies on the different spectral signatures or reflectance curves of different materials. So in the same way we have seen in the case of water, where atomic and molecular resonances were giving or were originating difference in the permittivities and reflections induced by these permittivity changes. The same happens with all other materials. So in this case, water is extremely low reflectivity material at optical and infrared regime, but if the water contains sediments, which is called so-called silty water, the presence of sediments will actually impact on the signature we can observe. So what we see here is a particular signature of certain sediments present in the water. Otherwise, that could be very low reflectance. In the case of, for example, a red sand cover, what we see here is the signature of this particular material, the type of cover. And in the case of vegetation, but what we see here typically in vegetation is a strong peak, reflectance peak, due to chlorophyll of the leaves, of the green part of the vegetation. And this has a peak around 0.8, 0.9 microns in the infrared, in the near infrared. We don't see at infrared frequencies. We see the plants and the leaves color green because there is a minor peak here around the green frequency, 0.5, 0.55, that corresponds to green color, but the strongest peak is not here, it's in the near infrared, where we cannot see, but remote sensing optical sensors, they can be designed in order to take a look to the near infrared, also medium and far infrared region. And this is an example of a spectral reflectance image, which is showing, in this case, in the Thames estuary, close to London, the pattern of sediments and how this sediment pattern is altered by the presence of these wind turbines. This point here is a network of wind turbines operating here, generating electricity here. At the presence of the towers, actually has some impact on the distribution of sediments, which is actually picked up with this image. Okay, another mechanism which can be used for remote sensing is the actually spontaneous electromagnetic radiation due to materials and actually due to the heat of materials and molecular and atomic structures. So when a material is cold, we can consider the position of atoms and molecules rather static, but when we increase temperature, there is a random motion which is becoming important with higher temperatures, and this random motion of particles, charged particles, results into an electromagnetic radiation, which can be weak at low temperatures. It is increasing very importantly at high temperatures, at thousands of Kelvin, for example, temperatures. But anyway, even at ambient temperatures, few hundreds of Kelvin, this radiation, although small, can be picked up by sensitive receivers. And actually, if we consider or we represent the spectral radiation or spectrum of this radiation, we can take the black body actually spectral brightness expression, which is this expression here, and if we plot it for different frequencies and different temperature of the material, we obtain this the so-called black body curves or radiation law curves, which actually show us what is the spectral density of this thermal emission. So you could see here that, for example, for 300 Kelvin, which is more or less ambient temperature, how is this radiation taking place? This has a peak in the infrared region, in the medium infrared region, but even at microwaves, this signal can be picked up by a sensitive receiver. And this is interesting because we can measure temperature of materials, and also we can measure what is the parameters related to permittivities and roughness of these materials. And why is that? Well, we have to take into account that these black body curves correspond to a perfect absorbing material. But in practice, most of natural surfaces are not perfect absorbers. They do reflect according to the incidence angle, the observation angle, and according to frequency and permittivities and permeabilities, they do reflect more or less electromagnetic radiation. So in case of not a black body but a reflective material, the emissivity of this material, or the thermal energy, is not so high as in this case, is substantially lower, and this brightness temperature can be measured and can be related to either the physical temperature of the surface or characteristics, dielectric and scattering characteristics of the surface. And this is interesting because it can provide information on, for example, gases, atmospheric gases, soil moisture, or salinity or wind distribution over the oceans. Let's take a look to one of these images. This is a brightness temperature image obtained by the SSMI sensor on board of the F-14 satellite from NOAA. And the brightness temperature image is calibrated in Kelvin. You see here the scale. And actually is showing us interesting features, for example, the ice distribution in the polar caps, north and south, and also some snow presence, and the presence also of water vapor composition, distribution in the atmosphere, rain events, and other particular phenomena of interest. Actually, these images are combined, different bands and different polarizations are combined in such a way parameters like rain distribution or wind over the ocean can be retrieved using suitable models. Now, to finish our presentation, I have included a couple of slides on the particularities or general particularities of the imaging process. What is imaging? Imaging is obtaining a representation of an electrical or physical parameter of an object, and actually the process to obtain an image is generically what is depicted here. The object is either radiating or scattering some sort of radiation, for example electromagnetic radiation. The sensor actually picks up this radiation by some aperture. This can be, for example, the primary mirror of a telescope, or can be an antenna, for example. We get here a receiver which is filtering and amplifier the information which is captured by this aperture, and then in some cases we need to apply an image reconstruction algorithm in order to transform these fields into an image. This is the case of synthetic aperture radar, for example, or radiometric interferometer. In this case, the image is never an exact reproduction of the original object properties. It's always going to be a low-pass version and some distortion, some noise corruption, and so on. So here what we intend here is to design better instruments, better reconstruction algorithms, better calibration procedures, and so forth, in order to get these images as much similar as the original properties of the objects we want to obtain. And in order to formulate this mathematically, actually we can consider two problems here, the direct and inverse problem. The direct problem is the mathematical models which relate the object with the fields which are being produced by this object. This has some difficulties, of course, in most of the cases, and so there is some effort being devoted by scientists in order to get better modeling for the direct problem. Because if we know well the direct problem, we can invert it, which means from the observed fields we go back to the original properties of the object producing those fields, and this is this inverse problem. So in the way we can actually know or model mathematically the direct problem, we can try to actually go the other way around and obtain the physical properties of the object from this. So this involves quite a lot of research on mathematical and physical modeling, taking into account the object characteristics, the type of radiation, the characteristics of the sensor, the imaging algorithm, and so forth. So there is a lot of effort in this kind of models. Now, suppose we are designing an instrument, a sensor which provides an image of our objects. How are we going to characterize the quality or the quality metrics of this instrument? Well, there are some basic measurements that we can do. A very important one is the spatial resolution. The spatial resolution means we have, for example, a test object which is just a point-like object, and we obtain an image after all the sensor chain. This image has not the shape of the original object, so normally we are going to lose resolution. So this point object, it does not appear as a point in the image, it appears as a kind of a lobe, a main lobe, but some side lobes. So now what are the metrics of this kind of response, which is called the point spread function of the sensor chain? Well, if we take a look to the point spread function, there are two or three basic parameters we can measure. One is the spatial resolution, which is the size of the main lobe. This size is actually measured normally at -3 dB points or drop cuts. And is actually a metric of the size of this lobe. So if we have two small objects inside this lobe, they cannot be distinguished. If these two objects are separated with a larger distance compared to the spatial resolution, they will be able to be distinguished by the sensor. So it is interesting to decreasing this spatial resolution to very thin values if you want to get very small details of the observed surface. Another parameter which is more subtle, and it's also very important, is what are the silos being produced. These silos are obviously not wanted because they can interfere with also minor features of our image. So we would like to get these silos as low as possible. So how are going to be measured? Well, we can just measure the peak side lobe, and we can compare the amplitude of the peak side lobe with the main lobe, and this is the so-called peak side lobe ratio, which can be expressed in dBs. That is quite simple to measure. However, if we want to measure the overall impact of side lobes, the peak side lobe is not a sufficient measurement, so we have to actually measure the energy which is contained in all the side lobes around the main lobe, and compare this energy with the energy of the main lobe. And this is actually the purpose of this expression. These two integrals compare the energy of the main lobe, the energy of the main lobe compared to the energy of the side lobes around the main lobe. And now, to finish our lecture, let's take a look to the added value chain of the remote sensing sector. We have, in order to actually provide data to final users and to get a market impact in the remote sensing sector, we have actually to feed the chain of value with proper data and activity, mathematical models, and transformation, geometric and radiometric transformation activities. So in the left side we have the sensor operators, either on board of satellites or airplanes. These sensors provide data. This is just a matrix of numbers, for example, but this data is still not information. We need to calibrate or to reconstruct, in some cases, images from this data, and in this way these numbers become information. But this information is normally a kind of electrical parameter, for example reflectance, or for example radar backscattering, or brightness temperature parameter, which is not useful for a final user. Here we have an agriculture here company which wants to know, I don't know, what is the soil moisture or the nitrogen content of the plant. So do we have to actually irrigate our terrain or not? We have to actually take care of a plague or a problem with some crops, and this could be also pollution, and it can be also meteorologists and many kind of users. So they are not interested in parameters like radar backscattering or brightness temperature. They want to know winds or water vapor and things like that. So how are we going to provide this final information? Well, this is an important stage. So we now have physical information which is calibrated, but now we need models. We need models in order to transform these physical parameters into geophysical parameters of interest to final users. And so we have to transform this data into images. And if we want that these images actually can be efficiently managed, for example, in a geographic information system, which is actually a geographic database, we have to provide maps with proper geometric corrections, and with proper projections following standards in mapping, like UTM projections or other projections of interest. And this is actually the role also of some people here in this activities of providing services and parameter extraction, and expressing all these parameters in a convenient way in form of maps. So in this way, by the combinations of engineers, scientists, mathematicians, and so on, and geodesists, this information can be provided in a way that is can be efficiently used by users. In this way, the market can actually develop. And so this is actually shown by these inequalities here. So data, primary data, is not information. It has to be transformed into information. Information is not knowledge in terms of geophysical parameters of interest. And finally, geophysical parameters is not necessarily wisdom. What is this wisdom here, what doing here in this slide? Well, finally, we can observe, for example, the increase of global warming, or, for example, the increase of CO2, or the loss of fossil ice in the polar caps. And okay, we can just do nothing, or we can just take some action on this. So this wisdom word here, what this means is, okay, providing data, calibrating data, and so forth is not sufficient. So we have to take action. We have to preserve our planet. We have to try to work not so much in the material side, and also to work more into the preservation of the planet for the sake of future generations. And this is the wisdom word here, and I would like to finish the presentation with this comment. The final slide contains some basic reference which are very useful in this introduction chapter. Some very relevant books for very important scientists that has provided excellent reference material for these introductory lessons. Also some basic electromagnetic books, and also some particular technologies like laser and microwave systems. Thank you very much. I hope you have enjoyed this introductory lecture, and I would like to invite you to follow the following modules of the course. Bye bye.